Hello and welcome to another Clojure study group. My name is John Stevenson and thank you again for joining me. This week we are going to talk about sequences, and it's like a very core part of Clojure. And an example is the list, and pretty much everything you write in Clojure is probably going to be in a list. And so it's good to kind of be very comfortable with what that is, what that means. And we're also going to do some 4Clojure challenges as well, which are specifically related to like playing around with sequences, so we can get more of a flavor for like what sequences do and how to interact with them as well. And there's also a huge number of functions that work very well with sequences inside the Clojure language, inside the main part, which is referred to as clojure.core. That's the namespace that contains all the functions that come with the Clojure language by default. Okay. And feel free to ask questions in the chat window, and if anybody comes on live, I'm happy to chat there as well. Let's oops, I didn't want to do that. Oh, there we go. Share, there we go. Present to everybody, there we go. So, so we're going to talk about sequences. Yes, so you should have the chat window. Oops, that's the wrong one. That's the wrong one. There we go. So feel free to put things into the chat, and I will try and keep up with them as well. And let's hide that. There we go. So sequences. So there is a definition. If you go to clojure.org, in the reference section, there's sequences. So here's one of the main parts. There's a whole bunch of other things in there as well that are really interesting, but let's focus on sequences. So it's saying, seek, which is like the function you can call, is it's kind of a logical list. So a list in most terms, most languages, is people are usually referring to a linked list. So you have, for example, a list of numbers. So you might have 1 and 2 and 3. Oops, I didn't. I have 1, 2, 3, 4, 5, and they're put into some kind of collection. So you can kind of deal with those numbers as a group. So we can put those into a list itself. So just round that with list. There we go. Let me just quote that so it doesn't complain that otherwise it'll try and call one as a function, which one isn't. So I've got all these numbers. It's in my collection. It's my collection. This collection type is a list, and it is it's a collection of numbers. So the way that Clojure and kind of most languages work with a list is, you go to the first value, and then the first value actually has a pointer to the next value, and so on and so on. And so you can basically traverse the list just by looking at the next number, and the next number also has a pointer to the next number, and then that number has a pointer to the next number, and so on and so on. So you hopefully get the idea. So rather than just jumping into the middle 3, you can't do that because there's no kind of sense of an index underneath here. So I can't just go to position 3 because like the list doesn't know what position 3 is. So what's the point of a list? Well, it's really simple. It's a really simple construct, and it's very good for doing some iteration without having to keep any state. So I mean, you can have, if you do use a list, if you use a vector, an array-like structure, you do the same thing, but you can jump to these numbers, because underneath these numbers there is an index. So 1 would be at index 0, and then 2 would be at index 1, and then 3 would be at index 2, and so on and so on and so on. So you could actually jump to any point in the vector just by using its index. So this is why if you've got a really long index, really long collection, it's more efficient to use a vector because you can jump around to certain places. Where if you've got like 100,000 elements in your list, then you pretty much have to go through all of the elements to be able to just, if you wanted to add something at the end, you'd have to go through all the 100,000 elements, which is going to take a little bit more time. With a vector, then you can just jump straight to the end. So a list is like really simple, but obviously then it's designed to be processed from the start onwards. If you do things like adding to the list, so constructing, say we want to construct a new list, and so we want to create a list. Oops, list, and we want to create it from 1. Then this is going to create as a list. Did I get that the wrong way around? I got that the wrong way around. There we go. Been conned too long. There we go. Is that right? Yes, you've got to do a value and then the collection. So that creates a list of 1. If there was already some values in there, then if we got 2, then this is going to produce a different result. Oh, sorry, it's my bad. Saturday morning, I haven't woken up yet. There we go. Hopefully you got some idea about what it is, but it's basically saying Java long cannot be cast to an I function. So it's basically trying to call this as a function. And the reason it's doing that is the same reason I put a quote here, is because it's trying to call 1 as a function argument. If you put something in a list, by default, it's going to try and call that as an argument. So if I want to stop, it's going to try and call 1 as a function. So if I want to try and stop that, I can use the quote symbol, which is the same as doing it's the same as doing it's the same as doing that as well. This is just a very common shortcut for calling the quote function around something, and obviously it's using a lot less characters, so it keeps your code a lot more concise doing it this way. So this will prevent Clojure from evaluating 1 as a function. It'll just use 1 as a value. So now if I just do and you can see it's adding it to the front of the to the list because that's the most efficient way to do it. And this works the same thing if you do construct, which is construct, or conj, which is conjoin. So it expects to have like so we have a let's have a list of 1, 2, 3, 4, and if we want to join 5 onto that list, then it will do so at the start of that list, because that's the most efficient way to do that. If you did conj with a vector, then it would add it to the end because the vector has an index, and it's more efficient to do that. So that's kind of the basics of sequences. So what's the point? Well, you can treat your collection as a sequence, and it allows you to do like some very common functions in a fairly consistent way. So you've got things like first, second, last, and rest, which is the more interesting one. So you can run all these functions on a collection, and for example, if we've got first of, let's do a vector, so I don't have to do the quote. It doesn't matter if it's a vector or a list, it will just work the same. So if I've got this, then it's just going to give me the first value of that. And then if I do the same thing for second, I hope you can guess what it's going to do already before I type it. Oops. And obviously it's getting 2, then last, is another. Then last, we'll also give, hopefully, work out what that one is. Oops. Fingers this morning. There we go. So just value out, so it gets the last value, and then rest is the kind of interesting one. So rest kind of obviously works with first quite a lot. So first is grabbing the first value, but if we did rest instead of first, then it's going to return the rest of the values except for the first one. Boom. So why is that useful? Well, it means that we can actually just iterate around a function as well. Iterate around a collection of values. So we can get the first one and do something with it, and then we can have a function that's calling itself, and it's going to pass the rest of the values there. So then the first value then would be 2, and so on and so on. So you'd have a simple function. So it's a function that's which has a collection. So we pass in a collection to the function, and it's going to do something interesting, hopefully, with that data, and then it's going to call itself. So let's call it recursive function. So we can call fun, and we can pass the rest of collection back to function, so it will actually just go round and round and round and round until there's nothing left. We could put in a clause here to kind of break out when there's nothing left in there, but it will basically iterate over a collection, and we don't have to keep track of where we are in the collection. We just keep on going until we have either some kind of condition we break out of, or we just come to the end of the collection. So it's a nice simple way to do kind of recursion in that way, without having the extra baggage you would normally have with an imperative language. So that's a little bit of an introduction. Let's see, was there anything else interesting on the page? And so there's quite a lot of talk. You may have heard of functional programming languages and Clojure being lazy, which means it doesn't straight away try and evaluate a piece of code. It will actually wait for some further instructions, some further context about what to do, how much to do. So if you've got if you want to generate a list of numbers, so for example, you want to generate, but you don't know how many you want. So like you've got a whole you want a whole collection of integers. You can use the range. There we go. I'd almost forgotten what that was then. You use a range function, but if you don't give the range function any arguments, then it's just going to return a lazy, as it says here, it's a lazy sequence of numbers starting from start to finish. But if you don't give it any values, it's just going to generate like an infinite sequence. If you don't actually want to fit an infinite sequence into your computer because you don't have enough memory for infinity, because it's quite a big number, but you can put something around this. You can put another function around it, and obviously the common example is something called take. So I'm going to take a number of elements, in this case 10, from whatever it is that from some function, from the result of calling some function. So we can do range. If we did range by itself, it would eventually blow up my computer. It would run out of memory allocation. But if I do take 10 around it, it will just generate a whole bunch of numbers for me up until 10. So it'll generate from 0 to infinity, but I'm only going to take the first 10, so range stops after I've taken 10 from there, so it doesn't keep going on and generating new values. It only generates the first 10 values here, not to 9. So yeah, so you can have you can kind of offset when you make the decision about how many numbers you want until you actually really know. So having a lazy sequence allows you to kind of say, I want a whole bunch of numbers, but at some point I might want 10, another point I might want 100, another point I might want 1,000. I can still have the same way of generating it, but I can take different values at different points in my program as well. So it allows me to kind of delay kind of hard coding, like range is just going to give me 10. So if I just did range 10, it would only ever give me 10. And so I couldn't take 12. I would, because I wouldn't have 12. I wouldn't get 12 numbers back. I'd only get 10. I'd only get the first 10. So without the range here, then I can do with 100, 1,000, whatever, however many you want, 101 kind of things. It's all going to work the same because range is just going to do whatever it needs to satisfy the outer expression. So that's a bit of insight into sequences. They're all lazy, and so the way it's been implemented in Clojure specifically, it's not just the list that is a sequence. As it says here, Clojure uses the iSequence interface, which allows many data structures to provide access to the elements of sequences. So typically you're using using lists and vectors to be able to do that as well. There's also this idea of transducers, but we'll come to that in a different Clojure study group. And you can actually use sequences lazily, and you can also specify something as being a lazy sequence as well. If it's so the opposite of lazy is either eager evaluation, so it's either lazy evaluation or eager evaluation. Some people will also call eager evaluation strong evaluation. So it's basically happening straight away. But if you want to prevent that and your function isn't lazy, you can also wrap your function inside a lazy sequence as well to do the same results. And we do have, there is some 4Clojure examples I'll cover in another session to show you that as well. But that's it. So in summary, a sequence is just a nice, simple abstraction over a collection of data, and you can do some common functions in there, and you can also treat it lazily as well, and can offset hard coding kind of decisions until later on in your program. So we've done some stuff around sequences here already. So we've already covered in earlier videos, we've covered things like challenge 21, where we used nth to kind of find the location of things inside a sequence. And then we've had one where we couldn't use nth, so we had to kind of, here we're taking a collection in and a number, and we're going to iterate through the collection. Well, we're going through the collection and getting the first one and dropping the number of collections. So we're actually stripping off the values by going through there. So we implemented nth there. And the more interesting one we did last time was counting a sequence, but without using the count function. And we basically just reduced all these. We went over the sequence, and we replaced all these values with a 1, and which is what the map constantly expression does. It basically goes over each element, so each element is represented by the percent sign. So we go over, we get 1 and we turn that into 1, we get 2, we turn that into 2, and then we do that, and we basically have a sequence full of 1s, and then we use reduce to add them up. So we basically use reduce to kind of say take each value and add them and use this function together, which this function is adding them together, and that's going to give us the value 5. And the same thing works for strings, because a string is a sequence of characters, and this is also a sequence of vectors which we add up. So we turn each one of these into ones. So we turn the vector into one, and same for keywords as well. So let's look at another one. So we've got reverse a sequence. So this would be quite simple if we could just use the reverse function. But unfortunately, we're not allowed to use the reverse function in this challenge because it's a special restriction. So we could take these. So I've started to write this down here in this reverse a sequence section. So this is a fairly easy one. It's not an elemental one, but it's a fairly easy one. If you've done the elemental ones, then hopefully you start to get a feel for these ones. So we've got some sequences here. So we've got a vector here that is just 1, 2, 3, 4, 5, and we're just going to reverse that into 5, 4, 3, 2, 1. We've got a sorted set, so it's going to sort the numbers and put them into a set, and then we just want to reverse that set. So obviously a set is going to create unique numbers. So let's just kind of copy that out and show you what that's doing. So a useful way to kind of understand what's going on is to actually just copy out some of the parts of the code. And here we've got just the sorted set part. So like, what does that actually do? So sets usually give unique values. So let's see about this. And so it has given unique values. So there's only 1, 7 in there. So instead of being 2, and it's sorted, it's in a numerical order. So instead of being 2, 5, 7, 7, it's just 2, 5, 7. It drops the extra 7 there because it's a set. It's all the values have to be unique. And then this one is just basically organizing the values inside the vectors in the reverse order as well. So it's kind of like that one, but just a little bit more complex. So it would be very easy to use the reverse function. So let's just see the reverse function in action. As you can probably see, it just reverses things. So reverse is just part of the clojure core, as you can see there, and it will just take it takes a collection and returns a sequence of the items in the reverse order. This one specifically says it's not lazy, so you'd have to wrap it in a lazy sequence if you wanted to make it lazy. In this case, we don't. It doesn't really matter that it's lazy or not. We would just want the answer. We don't want to. We just no need to kind of delay. So reverse, and then what was the? Oh yes, it was 1, 2, 3, 4, 5. And I'm pretty sure you've already guessed what this is going to look like because that's the answer there. So we could use that if we weren't denied the ability to use it. Oops. Yeah, if we weren't, if this wasn't a restricted value, a restricted function, then we could just use reverse. And we can do something similar with rseq as well. It was like it just creates a reverse sequence. So you've got you can call the seek function, and that is just going to returns the seek on the collection. If the collection is empty, it's going to return nil. And you've got rseq, which is just going to return a reverse of the collection, I imagine. Is it there? Yeah, so it just creates a sequence, but in reverse. And it could be a vector or a sorted map. And then just if there's nothing in there, it'll just return a I think so. If we give this another vector, 1, 2, 3, 4, 5, then rseq will let's put that back up here. Where was it? Oh, there we go. rseq then So those functions kind of work the same. I think if we looked at the code of reverse, then and the code of rseek, we might find a lot of similarities there as well. But unfortunately, we can't use either of those. So let's see what we've got there. No questions yet. So how do we actually create a sequence? Well, we've seen that already a little bit. So let's look at creating a sequence again. So we can construct a sequence. So as Clojure is immutable, we've got our sequence already, which is our 1 and 2 value in the list. And if we do cons 3, we construct it constructs a new sequence with all 3 values in it. And because it's a list, it's going to put that onto the start of the list because it's more efficient to do so. And then we can do the same thing with a vector as well. Yeah. So we can construct a list. So if we actually had a function that basically went through all of the values in our original sequence and constructed one by one a new sequence and put all the values at the front, then in fact it's actually just putting everything into reverse, because we would start off with we would create a new say we're creating a new list, we'd go through the values of 1, 2, 3, 4, 5, and we put one oh actually no, sorry, we'd put it was a list, and we'd put 1 in there, but then the next time we run cons, we'd put the next value, which is 2, at the start. So we'd have 2, 1, and then we'd have 3, 1, and so on and so on. So actually just creating a new sequence just by using cons, then or using a list, then we're always going to put it on the front. Therefore, automatically it's reversing the numbers for us as we go through the numbers 1, 2, 3, 4, 5, because they're all in order. Then as we build up the new sequence, then it's automatically putting them into reverse order for us. So we can use cons. We can also use conj as well. Conj does the same if we're using lists. So because conj is using the is aware of the implementation of the list, so it's going to put the value at the start of the list each time. But it's if you give it a vector which has got an index, it knows it can kind of put it at the end. So this does probably more what you're used to kind of seeing. So it's actually creating a new vector with the original 1 and 2 and adding 3, but this time at the end. And it's doing so because it's a vector, and the vector has an index, so it's performant to be able to add a value at a particular point in time. Whereas a list, it would be less efficient to do so. So those are kind of our options. We could actually use cons and conj to actually just build up through here. So we could actually have like here we can have conj 1 onto a list, then we get 1. If we conj 1 and then take the result of that and conj 2 onto the result, which is what we're doing here. So we're going to evaluate this conj 1 and get the results of 1, and then that result. So this will be replaced by a list containing 1, and then we can use that inside as an argument to the conj with 2, and it would add 2 to that. And then we can keep on going around here, but hopefully you get the idea of what it's doing. So we're going around and we're building up. So if we keep on giving it arguments of 1, 2, 3, 4, 5, it will keep on generating a reverse of that structure because it's adding things to the front of the list. And so we could write our own function to do this, right? Either a function that calls itself and keeps passing the values back to that, or we could do a loop recur. But there's also a nice function called reduce that does a lot of the work for us, so we can use that. So let's take let's just have an aside of a simple example of reduce. So here we basically want to add up all these numbers and come up with a single result. We can't just do, because this is a vector, because it's a collection, we can't just go in and just add the numbers together. Let's like this, 1, 2, 3, 4, 5. This is going to cause an error because yeah, it's looking for a plus wants arguments as numbers rather than actual collection. So we're actually just giving the plus function a collection here as a single argument. We actually want to give it the individual numbers in order for it to work. So let's just comment that out. I mean, we can't actually just use the plus function like this, 1, 2, 3, 4, 5. So it will take multiple numbers, but it wants the individual numbers. It doesn't want the actual numbers in a collection. It doesn't know how to process that properly because of the way it's implemented. So in order to get this same kind of result, we can use this reduce function. And reduce function will basically go through here and say, oh, I'll get the first number, and then it's going to add it. And then the second number, it's going to add it to the result of adding the first number, and so on and so on and so on and so on. So in the upshot is it will basically go over each of these and add them to each other and give us the total result. So if we do that one, we get 15 as well. And we can use that in the context of our reduce, like our conj. We can use conj with that as well. So we can conjoin each value in our collection to a list or to a vector or to a set, whatever we want to use. In this case, we're using a list. And it will just build up the list was. So using that, we've actually just solved at least the first test of the 4Clojure one. So we can use this reverse conj with a list, and it will actually just generate us the right result. And it doesn't matter that this is in a vector. When you're comparing with equals, then it's comparing the values inside the collection, not the collection types itself. The collection types are irrelevant in this case. We possibly have a solution that works. Let's just have a look at the alternatives. We could use reduce cons as well, although this is a bit tricky because of the signature of the way. So I hadn't found a nice way to do that. As you can see, I've done a few experiments and it doesn't quite work. So I haven't quite figured out how to make that work yet. And I think it's the way that, it's the way it's kind of implemented. If you go into Stack Overflow, there's a nice comparison of like showing you how reduce and apply, which both kind of work in the same thing. You can use it, reduce and apply, kind of to give you like the same kind of result. They work slightly differently, but I can, instead of do as well as doing reduce, also do apply in here as well. Just change the word apply. Oops. And if I do that, then it's giving me this. So it's working kind of the same on the surface, like logically, kind of tells you the same thing, but underneath it's actually working slightly different. But I'll cover that in a specific topic anyway. But if you want to have a look at your Stack Overflow question, then it's quite useful as well. I'll put all this code in link in the show notes so you can follow it all as well. So the upshot is I found it very difficult to use cons, whereas conj was actually just really easy, so I just stuck with that. I actually, to be honest, I use conj a lot more than I use cons in general Clojure stuff. So how do we actually put this? So we've got our answer where we're doing reduce by using the conj function. We want, and then we're giving that conj function arguments of we want to put it into a list, and then we want the values 1, 2, 3, 4, 5. So this is going to, so reduce is going to pick out this number, and then it's going to conj. It's going to go and put in here. It's going to put like, it's going to basically create like conj 1. So that'll be the first thing it does, and then around that it'll put another conj. That's it does the result of that as conj 2, so this would then do a conj of this previous expression, and then also do, but with the value 2, and the same thing with like conj, and they would do another conj with this, slap that in, there we go. I don't want to do that. But then with 3 and so on and so on, 3, 4, and 5, and this will give us, this will also give us the same answer as well. If we just evaluate this, we can see that as well. So this is starting to build up our sequence. So this this is the code we need. This is the code. This is like logically how it's going to actually work through the reduce. And I wonder if I can debug that. Will that work? Yes. Oh no, it doesn't work. There we go. Oops. Oh, okay. Yeah. That's not happy code. Oh yeah, and comment that out as well because it doesn't like that. Where do we get to? Oh, sorry for the scrolling. There we go. No, nearly that. There we go. There we go. So that's where we were. So reduce this. We can use this reduce conj with a list, and it's going to build. This is how it's going to work through everything and create as our list. So we just need to put that into somehow put that back into as an answer into our 4Clojure thing and fill in the blank. Oops. So we got a blank underneath here, which has got an answer already, which I won't show you just yet because it's slightly different. But so we want to define a function here. It's going to take a collection, and then it's going to reduce conj with the list over that collection. So this is a function, defined function that will give us the right answer. And then we can put that function, because we're using an inline function, a lambda as it were, then we have to basically put that into a list to be able to call it. So put it into this, we put extra bracket around it, so it'll call it with a list. And this time we're also giving an argument to the function as well. And so we can test it here to show that yes, it's still working. There's also a short form that she uses a clojure reader macro here. So basically, so instead of having to type function and the argument here, it's just assuming that there's a function. So this would expand to the above expression, and we just use this percent as to represent where the arguments go. So this is where the collection is in here. So instead of having collection, we can use the percent sign here to represent the same values that are coming in. So we can call this just like before. Essentially, yeah. So we can do this. We can include this function in here. So we could actually just put this function as the answer. Let's just grab that, and we could stick it in here where these dots are, and you can see it's already inside a list. So that function definition would be called. So let me just replace what was there with this function, paste that in, and then we can see if this is actually going to work. So let's just run this, and hopefully green, green, green. So it's working for all of those. So sometimes when I do the 4Clojure ones, I just try and get the easiest one to pass, and then see if it passes for the other tests as well. But sometimes that works, sometimes that doesn't. And so that's a simple one. I've got a golf score of 40. All that means is I've just used 40 characters to do that as well. You could make it smaller if you cared about that by just using like X, and that still would work. I get a slightly lower golf score, but it's probably slightly less readable. It's like, what does X mean? I've got a golf score of 22. Golf scores are a bit of fun. They're not really serious. They're not a serious evaluation of how good your code is. In fact, it's probably the antithesis of how good your code is. But there is another way to do this. So we've got this reduce conj thing, and you might see this quite a few times in Clojure, reduce conj. And actually, if we go and look at, reverse. So now we've got an answer. Let's go and have a look at see what else is there. So if we do Clojure reverse in the browser, and it's going to take us to Clojure docs. And Clojure docs tells us how reverse works essentially and gives us some alternatives. It's also suggesting rseek. And there are some examples about how to use it. There's not many because it's fairly straightforward. But the interesting thing is it's got a link to the actual source code. So this is a source code that's part of Clojure. And this is the clojure.core library. So basically the clojure.core library in just one very long file, which just make it easy to search through things as well. And this is the reverse function. Let's just make that a little bigger so it's easier to see. Boom, boom. And so look, surprise, surprise, it is, there's a bit of like documentation, and then this is just a bit of metadata to say when it was added. And so reverse takes an argument as a collection, and it's basically calling reduce conj onto a list of the collection. So it's pretty much the same as what we're doing. I think reduce one is just possibly an optimized or simplified version of reduce inside Clojure, which probably should be defined in here, I guess. We can find that reduce one. Oh, there's 46 instances of that. So it's probably defined somewhere, but I don't know where. That's not, because it's used quite a lot. There must be some kind of optimization there over the normal reduce, but I don't know where it's actually defined. But there we go. So that works, and there's nothing wrong with that. There is another abstraction over the reduce conj, and so if we can have a look at that. So there's the combination of reduce and conj is essentially what the into function is doing. So let's look at that. So we can use into instead of doing reduce and conj, and we can go into collection. So we can kind of like if we just make it even simpler. So instead of doing reduce conj and then a list and then our vector 1, 2, 3, 4, 5, we can actually go in and just make that simpler to read and just do into a list the collection 1, 2, 3, 4, 5, and that's going to work exactly the same as the reduce conj, and is kind of a nice abstraction over that. Get the same result. And you can use into for maps and for sets and for vectors as well. It's not just lists as well. So it's a very flexible little function to be able to build into a particular type of collection the result of some function. So you can have a function here. So you know, do like into there we go. Some collection, either a list or a map or a set or a vector, and then you like have some result of calling some function. We'll go into there as well. So it's a really nice little function that does that, and there's probably lots of examples we'll come across in further 4Clojure examples. So we can put this into our function. Oh, boom, boom. That wasn't a pun, honest. If it was, it would be terrible. So instead of just using reduce conj, we just put into in there, and we can call it function. It works the same, and we can also do the short form, which is the same there as well. Boom, boom, boom. So let's do that. Nope. So that's how we can test it. We actually, for the 4Clojure example, we just want the function definition. So we can just use that one. And then we can feed our ego by having a very low golf score. I'm just putting that in there, and it should work exactly the same as the other example. He says, hopefully, green, green, green. There we go. They're all green. And then we can go and see, oh, my golf score is only 10. So it is quite a nice way to do that if you're doing inline as like a kind of a one-off piece of code. But if you're calling an external, if you're calling a function already that's like a global function in that namespace, then using the long form, this is a little bit more readable for most people. This is a nice kind of terse version of that to use in very specific things here. So if you're using a defin somewhere to define a function that you want to use multiple times inside a namespace, then I think this is kind of like it's a nicer and more easily readable kind of approach. So we've got, so that answers question 23. I don't see any questions. I hope I haven't missed anything. Nope, no questions. So that's 23 solved. Let's have a quick look at 24, see if we've got time to do that. Sum it up. So here we've got a function which returns the sum of sequences of numbers. So this is just adding all those numbers together. Okay, and list is going to create a list of those things. So we're going to have a list of 0, -2, 5, and 5. So if we add 2 to 0, we're going to get -2. The add 5, you're going to get 3, and 5 to 3 is 8. So we start with 4, 5, 6, 7. We get -1. Yeah, so basically just want to iterate over a collection and add all the numbers up and get a result. Well, I think we've already done something like that already. And we actually so we want to iterate over a collection, so we can use the reduce or apply function. And then we just need to figure out what, oh, hello, Kitty. Kitty's done come to do some closure. And then we just reduce over a collection with a particular function. And in this case, we want the function to be plus. So this one's fairly straightforward, just reduce plus over that thing. So we put reduce plus over in here, and it will just add all our numbers up. So let's press the magic button and go see what the cat wants. What you doing, kitty? What you doing? You've already been fed. Yeah, you've already been fed. Did that work? Did it work? Did it work? Let's have a look. It worked. There we go. So I guess this one is just it's actually a lot simpler than the one we've just done. But hopefully it's simple because we've done things like the one we did previously as well. I don't think there's much to discuss on that one. 25. Find the odd numbers. Ooh, yes, let's do a quick one on that. So we'll do this one. This will be the last exercise I think we'll do, and then we'll end the broadcast. So write a function which returns only the odd numbers from a sequence. And let's see. Okay. Shush, kitty. There we go. Just remind him he's got food and he should be quiet now. There we go. I do believe I created a file for this one. Let's have a look. Let's save that. 25, did I do 25? I didn't do 25. Okay, well, let's correct 25. And this was called find the odd numbers. And oops. Numbers.clojure. There we go. And let's see. Oops. So we're going to find the odd numbers. These are all our tests. Oh, there's the answer down there just peeking up. Hopefully you can't see that just yet. Let's make this into comments so it doesn't interfere with our evaluation of closure. There we go. Okay, so these are our tests. Oh yeah, and we're still using sequences. So if we have, let's see, so we want the odd numbers. So let's take one of the easier ones, easy examples. So we've got a vector of numbers. And we can see we just want the odd ones. So we actually don't want 4 or 2, but we do want 1. We want 6. We could, in using reduce, if we use reduce, what could we use with that? There is some Boolean. There's some Boolean functions such as odd. So we did odd with 1. Then as it's a Boolean function, it's going to return a Boolean result. We can kind of see that because there's a naming convention that if something is a Boolean, then we put this question mark at the end of the name. That's not something that the Clojure reader interprets. It is purely just a developer convention, a naming convention that we use. So if we evaluate this, then we get true. And if we do odd for an even number, then we actually get different results, obviously, as we would expect. So if we evaluate that, then that's false. So if we do reduce over a collection, and we use, well, in this case, we want to see if there's any odd values. So we can use the odd function there with reduce, just like it would be, just like we've used plus with reduce. My cats are having a discussion, sorry. And then will this get us the answer? Oops. No, because odd doesn't take a collection as an argument. So it's basically saying wrong number of arguments passed to call odd. So I'd actually have to, let's make this a little bit bigger. There we go. There we go. Yep. So I would have to make this into a function. So this is an example where like using an inline function is quite useful. So I want to be able to reduce, and I'm going to create a function which is going to take a number, and then that's going to call odd on that number. And then we're going to have the number in here. So we put 4, 2, 1, 6. Oh, and I need some spaces. 6 space. So it's going to reduce is going to use this function here to oops. Can use this function over each of these elements in here to see if it's odd, and what value is that going to give us? Is that going to give us something that's useful? Oh, what have I done? Oh, no, what have I done? Huh. Oh, I've done something silly. What have I done wrong? What? Oh, yeah, sorry, it was. I haven't prepared this one at all, so I might be doing something absolutely silly. And what have I done wrong here? I'm doing something wrong. Oh, there we go. Oh, yeah, constantly is a weird one, Lucas. Yeah. Yes. I'm not sure why I was doing that. I was trying to show you odd, so it would give basically what I would expect it to return would be something like whoops, something like I can't use my keyboard now. There we go. Something like true. We give false, false, true, false. But I'm obviously missing something obvious that I'm doing. And yes, somebody's way ahead of me, Bobby. Bobby's way ahead of me. So the thing I was leading up to was what Bobby's just mentioned. Like a more interesting form of reduce is something called filter, and there's also something called drop, which is the opposite of filter. So we can filter something, and it will use a function over a collection and only return the things that actually match that collection as that function. So if the things that are only true from that collection. So if we filter odd over the collection of 4, 2, 1, 6, then hopefully it will give us the right answers. There we go. So it returns only the value in the collection that actually matches the result of calling this function that gives a true result. So all the other ones are dropped. And there's also the opposite of this, which is boom, drop. So you can use drop as well. So it will again do the reverse of filter, and what have we done wrong there? I'm sure that was working. Oops, yeah, there we go. Have I done something wrong there? Drop odd. Why is that not working? Is it drop, or have I forgotten what drop does? H. This is the fun of getting something. Oh no, it's not drop, is it? It's remove, isn't it? I think it's remove. Remove odd. Yes, fairly sure it's remove. There are there are about 600 functions in the clojure core to remember, and today I'm struggling to remember the right ones. Apologies. Let's evaluate this one. There we go. I got the right one. There we go. So that's what I was looking for. So filter and remove are really good. Really handy functions for just returning, basically transforming your collection. In this case, we've got a simple collection here, but you might have a more complex collection. You just want to return specific values from that match a certain criteria. And that criteria can be like a simple built-in function to clojure, like odd. You can also create your own function in here that would do something interesting. And Oh, no, it's not map. It's not reduce. Oh, I just realized what it is. It's map. There we go. That's the one I was looking for. So I don't want to reduce the values. I want to apply odd to each of those and see what the result was. I knew I was doing something silly. There we go. Yay. My brain has kicked in. Sorry about that. Yeah, so instead of reduce, it wants to be map. The map is going to apply something, a function, to each of the values and give you a result for each of those values. It's not trying to create a single value like reduces. So yeah, I can use map to basically process each of the elements in there. I think that's what I was trying to do. Yes, there we go. Oops. It is quite easy to get map and reduce mixed up when you're first starting as well, even when you've been doing it for quite a while, by the looks of things as well. So to get back to the challenge, so if we use a filter, and because they all want to reduce, they all want to return just the odd numbers, so we can use a filter of odd with all of these, and it should give us the right answer. So we go back to our 4Clojure stuff, and we can basically just put in filter odd. And if I'm feeling lucky, then hopefully, yes. Oh yeah, they're all passing. There we go. Cool. I'm not sure if there is another way to do that. I'm pretty sure there is one exercise in 4Clojure where you can use filter, but it doesn't let you use filter. So there's probably a different thing in there as well. Ooh. Oh, and this is using. Oh, this is. They've written their own odd function. So in this example, they've either not known about odd question mark or as a function, or they've just decided to create their own. So this is an example of using your own function with filter. I guess interesting stuff. There's a few people have done that as well. I really don't know why you need partial, but I guess okay, because it doesn't have the one in there. Okay. But yeah, most of these filter odd. It's pretty straightforward. Filter. That's another example of somebody. Yeah, so you can use the rem. So if you divide something by 2 and the remainder is equal to 1, that doesn't sound right. Oh yeah, sorry, yes, that's right. Yeah, so if you divide something by 2 and the value is 0, then that means that the value has got to be even because it divides by 2. If you divide something by 2 and then you get some remainder of 1, then yeah, that number is going to be odd. So that's their implementation of the odd function. Alrighty. I'm going to leave it there unless there are any more questions. There was another one. Oh, constantly. So there's a question about constantly for real life. I struggle with real life sometimes. So it's constantly, I think, I don't know if I've really used it outside of the context of the 4Clojure exercises. So here, if we go back to exercise 22, I use constantly. I guess in a way, it still kind of feels a little bit like cheating, because here I've used constantly just to replace all those values with 1. I guess if you want to reset values, if you want to keep the structure of a collection, but you just want to reset things to a particular value, and you want to iterate over that, then collectively, so constantly might be an interesting way to do that as well. Again, it's one of the functions I haven't really used hugely, but there's probably some niche kind of examples of where it could be quite useful in real life. My cats are having a real good discussion this morning. I'm going to have to go and sort them out. And I haven't used select. I'm going to go and see what select does. I'm using select. Select keys is another interesting one, but we'll come back to that when we do some more stuff with maps. Select odd from, oops, from the button. Select odd. from, oops, 4216. I have no idea what this does, but that's why we have a REPL. Oh, no, that doesn't work. Oh, it doesn't know what select is. Okay, right, so there isn't a select. Interesting. I wonder if select is from a different language. There we go. But I guess that's what you're trying to do. You want to select just the odd ones, the odd values from there, and instead of select, then we're using filter. I think the first time I used filter, I got a bit confused because I was wanting to filter, because I was thinking it was going to filter out the things that match the function, but what is filtering in. So basically saying filter only let things pass through that match the positive result, the true result of this function. So I think that kind of, I started thinking in the opposite way at first, so I was getting confused. But obviously you could also do filter as well as filter odd. You can filter with even as well. And let's see, even. And obviously this will just return the even results for you as well. So it's quite easy to do functions that do the opposite. And you can also do, if there wasn't an odd, you could put around complements of odd, and it would do the same thing as even. In fact, if we go and actually look at the source code for clojure odd, I have to go and sort my cats out because they're killing each other at the moment. Yeah, so here it's just doing not even. So it's just doing the inverse of even. So odd is actually not really a function at all, really. Okay, I'm going to leave it there because my cats are going absolutely mental for some reason this morning. But thanks very much for listening. And if you've got any suggestions about what to do next, please let me know. And thank you very much for listening. Okay, thank you. Bye-bye. Stop.